Would you look at that? Lecture number 20. Exam number 3 is now behind us, and we only have a few weeks before this class is over. Today, I'd like to review the power flow diagram, and then we'll move to DC machines, including the DC linear machine, which is really just a thought experiment, and then the conventional DC machine. From our discussions of transformers, you'll recall a power flow diagram. And the transformer had several losses associated with it, including I squared R losses in the primary winding and in the secondary winding. There were also losses in the core. Turns out that motors have the same losses plus a few more. Since motors have windings that are carrying current, we still have these I squared R losses. The terms will change, and I'm going to leave those blank because it depends on what type of motor you're talking about. For example, an AC induction motor would have losses in the stator. It would also have losses in the rotor. It would also have losses in the core. And then we'd have something called friction and windage. Friction because there are parts moving relative to each other, and windage because you typically have a fan, and that fan is blowing air across the motor to keep it cool. Either way, our descriptions remain the same. We still have a power in, we have a power out, we have an efficiency, which is defined as the power out over the power in. That can also be described as a power out over a power out plus a power lost, where this is the power out and these are the power lost. Together, they better equal the power in. Be careful. Not today, but in future lectures, we're going to talk about AC motors. And when we do, we're going to have these power triangles. Remember, it was P, Q, and S. When we talk about power, we're talking about the real power. So keep that in mind for future. While your note card is out, be sure to record this. 1 horsepower is equal to 746 watts. Also, 1 horsepower is equal to the torque, that's in foot-pounds, by the RPMs, over 5252. With that said, let's take a look at the linear DC machine. Conceptually, it looks something like this. We have the battery, we'll let that be 50 volts, a switch, which will close at time 0, and a resistance. We'll let that be 1 ohms. To that, we attach 2 absolutely perfect wires. And when we say perfect, that means wires that make perfect connection but have no resistance. To those wires, we're going to affix a bar. So we'll put a bar right here. This bar will make contact with the wires. It will make perfect contact. It won't spark, it won't slip, it will have a perfect electrical contact. We then assume a perfect uniform magnetic field across the entire page, with the understanding that both these perfect bars, right, these non-conductive bars that make perfect contact with the slider, continue off forever in this direction. Again, not something you can build, but conceptually something we can talk about. We'll let this field have a strength of 1 Tesla. We'll let this bar have a length of 0.3 meters. At this point, we're going to present a few equations that we're going to use to describe the motion in this thought experiment. The first is the force in the bar, right? The bar being this purple movable piece is equal to Bill, where B is the strength of the magnetic field. We define that as 1 Tesla. This is the current, and this is the length. We define the length as 0.3 meters. We have another equation. This one tells us that the voltage induced on the bar is equal to the B field by the velocity by the length. This is the equation that describes the force on the bar, and this is the equation that describes the voltage induced on the bar, where the bar is this purple piece that we are going to move. Again, it makes perfect contact on these 2 sliders that have no resistance and move in a uniform magnetic field. To understand what's going on, we're going to do this in 2 steps. We're going to assume the initial conditions, right? What happens when that switch is closed? And then we're going to see the final conditions. Where are we when that switch has been closed for a very long period of time? As far as initial conditions are concerned, what you see is what you get. We have the battery, we have the switch, which closes at time equals 0, and we have this bar, which is originally not moving. So we would say the velocity is equal to 0. The voltage across the bar, let's see, do we have an equation for voltage induced on the bar? The voltage induced on the bar is going to be 0 because the velocity is 0. So the voltage induced is 0. The force on the bar, let's see, the force on the bar is a function of the B field. We know that to be 1 Tesla. It's a function of the current. We can calculate that. That's easy. And then the length of the bar, we know that to be 0.3 meters. The current, when the bar is here in this position and not moving, that means there's 0 voltage developed across these rails. If you do Kirchhoff's voltage law, you would see that there's 50 volts at the battery, and all 50 volts must be dropped across the resistor because this is 0. When we go back here, we can talk about the current. That current will equal the battery voltage, so that's volt source divided by the resistance. In this case, it's 50 divided by 1, so that's 50 amps. The force on the bar will equal B by the current by the length. So force on the bar is equal to 1 Tesla by 50 amps by 0.3. So we could talk about the force on the bar equaling 15 newtons, which works out to be about 3.4 pounds. But in which direction? The force will be moving the bar in this direction. How do we know that? There's something called the right-hand rule. When you look up right-hand rule, you're going to find something that looks like this. You're going to see a right angle formed by these vectors, and you're going to see a right angle formed by these vectors. Now that's fine, but it's a bit hard to do on a screen like this. So I'm going to simplify it a bit. We're going to form your hand like so, and you're going to point with your fingers. as if you were shooting an arrow. So whichever way the magnetic vector goes is the way you're going to shoot. So if you have into the page, right? If your vector is like that, you will go into the page. Next, you will orient your hand, actually your thumb, in the direction of the current flow. So I'm assuming the current is flowing this direction, right? This direction here. I'm assuming the current flowing that way. And then wherever your palm is, that's the way you will move. Okay, so if I assume the magnetic field was straight up, I would point like that. If there was a current carrying wire and the current was flowing in this direction, so the current would flow from here to here, the force on the bar would be in. Okay? So if you do that, and we come back to this, you can say, well, I'm going to orient myself to the magnetic field. For you, that would be straight into the page. Not for me, because I'm in your page, but you'll point your fingers straight into the page. Then the current, in this case, let's see, the current would be flowing out of the battery like so. So that means you now have to point your thumb so it's down, and then you'll see the force moves you in that direction. With that force on the bar is going to start to move. As a function of time, it looks something like this. So this is velocity. So we start out with an initial velocity of 0, and we have some final velocity. Let's go back and see if we can figure out what that final velocity is. And it goes something like this. When we reach the final velocity, the force on the bar must equal 0. That seems like a strange statement, but it has to be. Because if the force on the bar wasn't 0, the bar would still be accelerating. So the force on the bar has to be 0, which means the current must be equal to 0. So we come over here and we start talking about our final conditions. So we said our current must equal 0, because if our current wasn't 0, we would be accelerating the bar. So final conditions, current 0. Our voltage induced must be equal to the battery voltage. So if you come over here, the voltage that's induced on the bar must be equal to the battery. If it wasn't, then there would be a current flow, right? If we did Kirchhoff's voltage law and we said this was 50 volts, and if we said this here was 50 volts, then there must be 0 current flow in that resistor. And we also said the force on the bar was equal to 0. If we go back and we pick up this equation here, the induced voltage is the B field by the velocity by the length. So the induced voltage is equal to BVL. We said the battery and the induced voltage must be the same. So our B field was 1 Tesla, our velocity is our thing of interest, and our length is 0.3. Solving for velocity, about 167 meters per second, which works out to about 374 miles per hour. So our final velocity is about 374 mph. We started out at 0, and we quickly reached 374. If you're curious, we could talk about the voltage and current. The induced voltage would do something like this, whereas the current would do something like this. You should also know that the force on the bar does the same thing. So this is force bar. Remember, our force was the B field by the time varying current by the length. B is fixed, L is fixed, therefore force is proportional to current. And you can see that here, the force on the bar shares the same shape as the current. From our voltage equation, that is B by velocity by L. Again, B and L are fixed. Therefore, the induced voltage is proportional to the velocity. So there's the velocity, and there's the induced voltage. They look similar. Well, that's all well and good, but our conversation is missing something. And the piece that's missing is we haven't done any useful work because we haven't had this bar work against something. So what I propose is that we push the bar. We push the bar so that the final velocity is, so velocity final, we're going to push the bar so that that is 200 meters per second. Okay, so we're going to push it, and we're going to push it faster than it originally would have gone. Because remember, here, where'd it go? Here we said that the bar was only going 167. We're going to push it so that it runs at 200. And let's see what we can see. So first, remember this equation here. The induced voltage is BVL. So the induced voltage is BVL. That's 1 Tesla. And we said 200 meters per second. And it has a length that hasn't changed. So the induced voltage is equal to 60 volts. You'll notice that that is greater, the induced voltage is greater than the battery. Which means in pushing this bar, we have made the system operate as a generator. Our current is 60 volts minus 50 volts. So that's the difference between the induced voltage and the battery, divided by 1 ohm, which means our current is 10 amps. By pushing the bar, by pushing this bar in this direction at a rate of 200 meters per second, we have made a battery charger. And the current will flow this way. I'll leave it to you to do the homework set where you see what happens when this operates as a motor. As for the rest of our conversation here, we're going to take all of these thoughts. We're going to take this thought experiment, which was a linear machine, and we're going to make it into a rotary machine. We're going to define some new terms. We're going to call this part the armature. This is where you'll find the output shaft of the machine. We're going to call that P out shaft. This is the field winding. The armature resistance, the field resistance, the terminal voltage for the entire machine, and the field voltage for the machine. As far as the field is concerned, we have a voltage, the field voltage, is equal to the resistance of the field by the current on the field. So we're basically saying that this coil at DC has 0 voltage drop across it. The armature has an induced voltage which is equal to some motor constant, phi, and then omega m. We would call this the machine constant, the field strength, and this is the rotational velocity. This has another name. We're going to call that the back electromotive force. So back EMF. If you squint at this equation just the right way, it should look familiar because the induced voltage on our linear machine was B, V, L. So here we had a velocity, so that's the velocity. We had the B field, which is the field strength, and we had the length. And length is just one of the things that we talk about when we talk about a machine constant. It's how physically large is the machine? How many coils of wire does it have? How are the wires connected together internally? Those are all things that go into the machine constant. Again, K, phi, omega, it's the machine constant, the field strength, and then the rotational velocity. Looking back at our model, the back EMF would be the voltage here. Keep in mind that that's a conceptual voltage. You cannot actually physically go in and say, yep, there it is. There's the back EMF, because you can't access that point. I mean, think about it. This resistance is the resistance of the wire that's on the motor, and that wire, of course, is distributed, so there would be no place to put a voltmeter to measure back EMF. Here's a few more equations for you. The torque on this machine is the motor constant by phi by the current in the armature. The power output of the machine is the velocity, so omega m, by the torque, which for our purposes will be foot-pounds by RPM divided by 52. The power out expressed electrically is the back EMF by the current. And when you look at all this, you'll find out that things are very similar to our linear motor. Our torque is proportional to the current that's flowing in the armature, and our back EMF is proportional to the RPMs. Personally, I think this is one of the more interesting equations. We go back to our model. It tells us that the output power is equal to the back EMF by the current. The current, well, that's pretty easy. The back EMF is conceptually here. So the power out is measured on the output shaft of the motor is back EMF by the current. And we said that the back EMF is proportional to velocity. I think that's what we said, right? Yep, back EMF is proportional to velocity. So tell you what, let's work an example or two and see if we can make some sense of this. We'll assume the resistance on the field is 500 ohms, and the resistance on the armature is 1.5 ohms. We'll let the back EMF equal 160 volts. We'll assume 3 horsepower output at 3,000 RPM. Let's see if we can find the terminal voltage and the current that's flowing into this machine. So we start very similar to our transformers. We work this problem right to left. So our power out is equal to the product of our back EMF by the current. Now this is 3 horsepower, so 3 times 746 gives us, what is that, 2238? So 2238 is equal to 160 by the current. Our current is therefore equal to about 14 amps. So that's 14 amps flowing here. That moves us to this point in the problem, where we can talk about the terminal voltage is equal to the back EMF plus IARA. So the terminal voltage is equal to 160 plus our current, we said that was 14 amps by 1.5 ohms. Terminal voltage, so that's 14 times 1.5 plus 160. So about 180 volts DC is going into this machine. So 180 volts. And now the current. You got to be careful with the current. True, it's 14 amps. It's 14 amps in this direction, but we have to also calculate what's going into the field. So that's not too hard because we know there's 180 volts across that. So we just say the current in the field is 180 divided by the resistance of the field, which is 500. So 180 divided by 500 gives us a current of about 36 milliamps. So that's 36 milliamps in this direction, which means the input must be about 14.4 milliamps into the machine. I hope that problem wasn't too bad, although it should have felt very familiar. Working the problem right to left and all of the steps you did should have been very reminiscent to the transformer work that we did earlier. Before we finish our discussion, let's change the operating conditions of this machine. Right now, the machine is spinning at 3,000 RPM and it's producing 3 horsepower. Let's add a load so that the machine is now spinning at 2,500 RPM. Find the new horsepower. To answer that question, we have to pull up this equation. So the back EMF is K phi omega. From our initial operating conditions, we were told the back EMF is 160 volts and the speed of the motor is 3,000 RPM. So we can drop those numbers into this equation. So 160 is equal to some motor constant by some B field by 3,000 RPM. If we were to solve that, we would say that the motor constant by the B field is equal to 160 divided by 3,000. So that's 0.0533. Consider this. We do not know what the motor constant is. We do not know what the field coil was set to. However, we know a few things. We'll assume that the terminal voltage hasn't changed, and we'll assume that we're using the same physical machine. If that's true, neither K nor phi have changed, so they're going to be constant. Now watch this. This equation didn't change, but what did change was the speed at which the motor was turning. Our back EMF is K phi, which is 0.0533 by the new velocity of the motor, which is 2,500 RPM. So our back EMF is now this number multiplied by 2,500. So our back EMF is now 133 volts. Okay, so that's simple enough. Our back EMF, which is measured right here, is now 133 volts. Can you calculate the current? And I think we can do that because we know that there's 180 volts here, there's 133 volts there, and there's 1.5 ohms. So our current, that's in the armature, is 181 minus 133 divided by 1.5. The armature current is 181 minus 133 divided by 1.5 ohms. So that's now 32 amps. So when we added our load, our current went from what it was initially. It went from 14 amps, and it's now 32 amps. The output power is the current by the back EMF. So our output power is 32 amps by 133 volts times 133. That gives you 4.26 kW. And we multiply that by 746 watts per horsepower. Gives you a power output of about 5.7 horsepower. So what was originally 3 horsepower when we were spinning 3,000 RPMs is now 5.7 horsepower when you're turning 2,500 RPM. And the secret to this problem, and the secret to your homework, is to remember that K phi did not change. Right? We had constant operation. We had a constant current on the field by virtue of having a constant terminal voltage, and we didn't change the physical machine. Everything stayed the same. All we did was change the load.